All right, so the plan for today is to finish section 2.7, so last couple problems there, and then to go through a review of chapter 2, just to um, you know to basically go back through, work through one or so problems of each of the types we work through. Maybe not kind of the simpler introductory problems, but go through several of these problems and just review what we actually learn in chapter 2. I think that's a good exercise to do. We might not do this every chapter. It'll depend on where we're at as far as the schedule goes, but we have a little bit of margin in the schedule right now, so I think this is a good use of this time. In future chapters, if we don't do this, if we don't end up doing a review at the end of the chapter, it's good for you to kind of take time and do that. You can either use some of the resources on WebAssign, or you can just go back through your notes, write out some of the problems that we did, just the problem statement, and make yourself kind of like a little like mini quiz kind of thing and try to work through the problems. And then you have your notes to refer back to see if everything, if you got everything right, or if you got stuck on a problem, you can refer back to your notes and figure out where you got stuck. So the quote of the day is, it's a quote that's attributed to Albert Einstein, but when you're somebody like Albert Einstein, people start attributing lots of things to you. So I'm not 100% sure if he actually said or wrote this, or if he was the first one to come up with this. Warren Buffett has said this before, and I think he's maybe even attributed it to Einstein. But the idea that compound interest is the most powerful force in the universe. And I think there's maybe a literal component to this, but also a component that applies in other places. So if you know anything about investing, you know that the longer term you invest for, the better it is. We talked a little bit about that in the simple interest I equals PRT formula. But also, usually when we invest, we get compounding. So the interest that we earned in the first year, that's put into our account, and then that interest gains interest for the second year, and the interest from the second year, as well as the interest from the first year, gains interest during the third year. So you get to stack these positive changes. So making small improvements that stack is typically much better across a lot of different aspects of life than making very large improvements that don't really stack, that don't really contribute to each other. So, one example of this might be something like studying for a half an hour a day every day, even if that accumulates only 3 hours of studying or so for a whole week, 3.5 hours, say, for a whole week. That's better than like studying 6 hours on one day. It's better to chip away at your homework half an hour a day than to spend, whatever, 6 o'clock to midnight on Sunday night trying to get through all of your homework. So this idea of, with say homework or with studying, learning a little bit, working a little bit, and then giving that a day to kind of settle in a sense, give it a day to for you to step away from it, come back to it. Maybe when you come back to it, you have a different idea, or you have a fresh approach. You can imagine at the end of a 6 hour, marathon homework session, after, hour 2 or 3, you're probably not going to be very alert and very interested in continuing on. So also note that positive feedback, in math, we call this positive feedback, in the sense that going a certain direction makes you more likely to go that direction, kind of. So this positive feedback can cut either way. So a lot of times we think of it as being something beneficial, but it can also be very dangerous. So just to take the financial example, something like compound interest, if you're investing money and getting compound interest, that's great. You're making a whole bunch of money over a long period of time. But if you have a bunch of money on your credit card and you let that money just sit there for a long time, well, now that compound interest is cutting against you. So especially when you're dealing with things that compound, whether it's in finances, whether it's in academics, whether it's just in life in general. Use it wisely. Okay, so we'll do a couple problems in section 2.7 and then jump into the review. So let's look at this inequality. Last time, just to super quickly recap what we did last time, just to remember what we talked about. We talked about inequalities, ways to represent them algebraically, like x greater than or equal to 0, as an interval, like closed 0 to infinity, and on a number line. We also solved several inequalities where we used the addition or subtraction property of equations, and we just applied that to inequalities. And we didn't give a whole lot of rationale for why we ought to be able to do that. Like, I mean, we know that this worked for an equation, but why does this work for an inequality? Well, if we think of that kind of scale analogy, you can tell I'm not an artist. This is my scale. If I have some amount that I don't know and -1, so somebody's pushing up on here with 1 unit of force, and I have 2 units of mass on the other side, and if I'm saying the left side is greater than the right side, that means that my scale ends up tilted this way. Now, if I add 1 unit of mass to both sides, if I add, say 1 unit coin, one kilogram coin or whatever to both sides, that doesn't change that. It's still the left side is heavier than the right side. If I subtract something, if I took away one of those coins from both sides, it doesn't change anything. So we can see that the addition and subtraction property still hold in inequalities. The other way we could think about it is that we're just taking the solution set. Let's say if we wanted to go this way, going backwards, x bigger than 3 looks like this with an open circle. If I were to subtract 1 from both sides to go the opposite direction to get up to this original inequality, well, that's just saying x -1 is greater than 2. So that's just coming down to 2 here. And if this was x, this is x -1. So we're, in terms of the graphical representation of the solution, we're just kind of shifting left and right, and that doesn't affect that inequality. Personally, I kind of like this view a little bit better. So like if I have the amount of money on the left and somebody else has the amount of money on the right, and we have this little coin purse here that we're not sure how much money is in it, if the scale tilts to the left, then I have more money than that other person. And if you give each of us another $1, I still have more money than the other person. If you take $5 away from each of us, I still have more money than the other person, right? We also looked at solving an inequality like this. So 5x less than or equal to 10. So if I have my, scale again, I'll try to draw my plates a little bit bigger this time so it's easier to see. So 5x means I have 5 unknown boxes. And on the other side, we have 10 coins. And 5x is less than or equal to 10. So let's just visualize it as less than. So my scale is Oops, wrong direction. 5x is on this side, 10 is over there. So 5x is less than 10. So my scale is tilted to the right this time. 5x less than 10. If I divide by 5, in other words, if I say, okay, what is 1/5 of what's on the left side? That's just a single one of those unknown boxes versus what's 1/5 of what's on the right side. Well, that's two of these coins, two of these units of mass. That should still be maintained, right? In other words, I can allocate to each box 2 coins. And if the right side is heavier than the left side for 5 boxes versus 10 coins, that has to be true for each 1 box versus 2 coins. That happens 5 times over. So when I divide by 5, it makes sense that if I say the person on the right has more money than the person on the left, if you divided each of their money in 5, then the person on the right still has more money than the person on the left. And let's look at this inequality. We're going to solve this 2 ways. The first way might look a little silly at first, but I think in a minute we'll see why we're going to solve it this way first. So I'm going to choose to solve this inequality with the addition property of inequalities, which we just kind of argued should legitimately work. We used it last time. We gave, I think, an argument as to why it makes sense for it to work. So I'm going to add 5x to both sides. And then I'm going to subtract 10 from both sides. Oh, geez. I'm having issues with my directions today, aren't I? I'm going to add 10 to both sides. So now I have 5x is bigger than 10. And now, just like last time, I'm going to divide by 5. And this gives me x bigger than 2. This is very reminiscent of this last problem, right? We got a 5x and a 10. We just divided through by 5. Same kind of argument there. So x bigger than 2. This is kind of interesting because here, x is on the bigger than side, whereas here, the x term was on the less than side. It was on the smaller side. So if I come over here, if I try to solve a different way, if I try to just naively use that division property that I used on the in the last lecture when it was, what was it, 5x less than or equal to 10, something like that. If I divide by -5, which would be a perfectly fine thing to do for an equality, but what about an inequality? If I divide by -5, -10 over -5 is a +2. I get 2 different answers here. What's going on? Well, it turns out that this is the right answer and this is the wrong answer. So just make sure to note that in your notes. I don't want you looking back through your notes and thinking that both answers are right or something. So just make sure to note that this is the right answer, x bigger than 2. This is the wrong answer. But why would this be the wrong answer? What did we do here that is kind of fundamentally incorrect? Let's again think of our scales over here. And we could start down here at, say, x bigger than 2. If I have a little box of with an unknown number of coins in it. And I have 2 coins over here. X is bigger than 2, so this right side is going to be heavier, like this, right? X is bigger than 2. I could have then that 5x is bigger than 2, right? I could see that 5 of these boxes of unknown quantity are going to be bigger than 5 lots of 2 of these coins. I think that's pretty clear for the same thing we talked about with that last lecture. So we could have 5 boxes over here and 10 coins over here. So 10 less than 5x. That makes sense. But now what happens if I put a negative in front of these? So what making these negative does, how you can kind of think of it, is instead of me owning these 5 boxes, instead of another person owning these 10 coins, now maybe they owe them. So if I have negative, if I kind of own negative 10 coins, it's a little bit like me owing somebody having a debt of 10 coins. Well, would you rather have, a debt of 2 units or a debt of the bigger absolute units? Well, I'd rather have the smaller debt, right? So when we multiply through by a negative, or for that matter, divide through by a negative, we have to switch the sign. I like to think of it, maybe because of my background is finance, I like to think of it as switching from owning something to owing something, or vice versa. That's why I have to switch the sign, right? I'd rather own $100 than $50, but I'd rather owe $50 than $100. And I mean, there are other ways you can think about it that are more abstract, or, you can really argue it directly with a method like A here. But I personally, I like the kind of finance analogy, own versus owe, or possessions versus debt. When you multiply through by a negative or divide through by a negative, you're switching from one to the other. And so the preference, in a sense, changes. I would prefer to have $100 in my pocket versus 50, but I prefer to have $50 balance on my credit card rather than 100. So maybe that makes a little bit of sense. And of course, you can always just memorize the rule. I try to avoid memorizing lots of rules, because if it's disconnected from where it came from, it's really hard to generalize to new settings, and it's easy to forget. But the rule goes something like, when we multiply or divide by a negative number, we switch the sign. So over here, what I should have done, when I divided by -5, -5x over -5 is x. I'm allowed to divide through by -5. There's nothing wrong with that. -10 divided by -5 is 2. But because I divided through by a negative, the less than sign, the inequality pointing to the left, becomes an inequality pointing to the right. And we do see that now these two agree, right? The x is on the bigger side of the inequality, the 2 is on the smaller side, even though they're written backwards of one another. That doesn't matter, it's the same inequality. So a few different ways you can think about it. You can think about it geometrically, like that arrow kind of flipping directions. You can think about it in terms of finance, how much do you own versus how much do you owe when you're multiplying by that negative. You can think about it in terms of using the addition property and wanting consistency with the addition property. Or you can just kind of memorize the rule. All right, so let's, as a practice, work through this one. This should only take maybe a minute or so. So solve this one two ways, using the addition property to make the coefficient positive and then divide. And then by directly dividing and being careful with that rule. So I'll give you maybe a minute and a half. Okay, so let's check in with this one. One way we could solve it is to make this coefficient positive by adding 3x to both sides. So that goes away on the left side, and on the right side, we'll have a 3x. And then we want to put the 9 on the other side. So instead of negative 3x bigger than 9, we have 3x less than negative 9. Then we divide through by the positive coefficient 3. We have x less than negative 3. We could write this on a number line. Like this. Or we could write this in interval notation like that. And the slightly quicker way to solve it is we can divide through by negative 3, completing this in one step instead of 2 steps. On the left, that gives me an x. My greater than sign, well, I divided through by a negative, so I need to flip that to a less than sign. So that's my step that I don't want to forget. And then 9 divided by negative 3 is negative 3. And we would have the same graphing or interval notation. Any questions on that? So this is one of those really annoying little rules that, you might do 10 of them perfectly the right way, and then you just kind of, it slips your mind for one problem and you forget about it. It's one of those things that just becomes a little more second nature with practice. But when you divide through by a negative, when there's an inequality, we need to switch the inequality. Okay, and then let's look at this one. So we're going to go through solving this inequality. We want to follow the same steps, as in solving equations. So we would first look for, say, any fractions or decimals that we might want to clear. I don't see anything here. Then we want to simplify both sides. So on the right side, I have something that's already pretty simple. There's no real like terms to combine. There's no parentheses to multiply out. But on the left side, I can do some work. I can distribute the 5 into my parentheses. Then I can combine like terms. And at this point, I have a choice of where to put my x. Do I want to put my x terms on the left or on the right? I could put them on the right. There's no problem with that. And I would end up with some number bigger than or equal to negative 22x. But if I look ahead, if I strategize a little bit, if I think a step or two ahead, now I have to divide by negative 22. If I set myself up, if I put myself in a position where I have to divide by a negative, that's one more thing I have to remember to do. I have to remember to switch the sign. That's one more place I could make an error. That's one more mistake I could make. And I'd rather set myself up kind of for success by setting myself up from the beginning, by putting myself in a position from the beginning where I have fewer opportunities to make a mistake. So if I choose instead to put my x's on the left side, that's going to give me a 22x on the left side. That's a positive coefficient. When I divide through by it, I don't have to remember to switch the inequality. I don't want to switch the inequality here. This would be my preferred option. I would always take the smaller coefficient, the term, the variable term with the smaller coefficient, and I would move that one. So here, smaller in the sense that if we have a negative number, negative numbers are always smaller than positive numbers. So I'll move the negative over to the positive side. That gives me a positive coefficient. These go away. My inequality sign stays the same. Get my constant terms onto the other side. Now I can divide through by 22. And I get x bigger than or equal to 27 over 22. So this is my preference. Anytime I'm solving a reasonably complex inequality like this, or I suppose like this one, I'm going to have a choice of which side to put my variable term on. And personally, I always choose the side that gives me the positive coefficient in the end. I choose to move the smaller coefficient term to the side of the bigger coefficient term. Then I always end up with a positive coefficient. And when I divide through, I don't have to remember to switch the sign. I don't have that one extra step, that one extra little thing I have to remember that's really easy to forget. So I try to think of things like this that I can do to reduce my chance of making an error, right? One way to reduce the number of errors you make is to just practice lots of problems so that you, for instance, maybe don't forget to switch the sign when you divide through by a negative as often. But another way to reduce errors, or a way that works in conjunction with that one, is to try to avoid those kind of situations altogether, right? So let's work through this one. I'll give you maybe 3 minutes to work through this one. and then we'll come back and wrap this up and then move on to the review. Okay, so the first thing we want to do again is simplify that left-hand side. That simplifies down to 11x plus 3 after we multiply out combined like terms. Then we have to decide what side we want to get the variable term on. And I always prefer to move the term with the lowest coefficient, the smallest coefficient. So a negative number is always smaller than a positive. So I'll move the negative 3x term to the other side. I add 3x to both sides. I move the constant term to the other side, and I get 14x less than or equal to negative 2. So sign stays the same here. We've isolated the variable term. We want to isolate the variable. We divide by 14. And again, because 14 is a positive number, the sign stays the same. I get x less than or equal to negative 2 over 14. And then I see that just like in equations, when I get to this final result, I should look for any simplifications I can make. And in this case, I can divide out a factor of 2. So x less than or equal to negative 1/7. That would be my solution. I could write this in graphical notation, or in interval notation, or leave it in algebraic notation, just depending on what the problem asks. So are there any questions so far on any of this inequality stuff? Okay. So we're going to move on then to the review. And I have, somewhere in the ballpark of 10 or so questions here. And this is what we're going to plan to do for the next hour or so. So probably what I'll do is just give you, a few minutes at a time for each of these problems, and then we'll come back and we'll work through each of them. So I think what we'll do is we'll start with these first two. So work through the first two will take about 5 minutes to work through these ones. And in 5 minutes, we'll come back and we'll work through them together. If you're ahead of the game, if you finish these both up within 5 minutes, I'll leave these other ones on the screen so you can work ahead if you want to. But if you're, right at pace, if you're completing these two within 5 minutes, more or less, or if you're, pretty much most of the way done after 5 minutes, then you're right on track. So we'll take about 5 minutes, come back, and then talk about these two. Okay, let's work through these two. All right, so the first one, we see the left side and the right side look pretty complicated. So let's start by distributing everywhere we can. So on the left side, I have 5x minus 5 minus 4x. On the right side, I have 3x plus 9. And I'm going to be super careful here. This whole minus 3 gets distributed. So I have a minus 3x. And then I have minus 3 times negative 1 is plus 3. I've got all of my parentheses gone. I've done all of my distributive properties that I can do. And now I'll combine like terms. 5x minus 4x is just x minus 5. On the right, I have 3x minus 3x. They actually go away. 9 plus 3 is 12. So a whole lot of work to get down to x minus 5 equals 12. And now we see we have one equation solving step to do. If we isolate the variable term, because the coefficient of the variable is 1, I don't have to isolate the variable, just isolating the variable term gets me the answer. And for good form, because we haven't done it in a little while, let's plug back in and check. Right, a good idea to do on an exam when we have, especially if we have a little bit of extra time. Okay, did I copy all that down right? 3 times 17 minus 1 minus 4 times 17 equals, we'll put a question mark here, 3 times 17 plus 3 minus 3 times 17 minus 1. I'll start by simplifying my parentheses. I got to remember order of operations. So multiplication comes before addition, subtraction. 5 times 16 is 80. 4 times 17, well, that's like 4 times 10 plus 4 times 7. That's one quick way to do it. So 40 plus 28 is 68. 3 times 20 is 60. And 3 times 16, again, that's going to be 3 times 10 plus 3 times 6, or that's 30 plus 18 is 48. 80 minus 68 is 12. 60 minus 48 is 12. And we've checked that x equals 17 is actually the solution. So for the next one, we had just a single variable term up here, and we had to isolate the variable term by moving the constant to the other side. Here we have two variable terms, one constant term. We want to isolate the variable term again, but this time we'll move the variables together. And this is a pretty straightforward one. As soon as I subtract off the 15x from both sides, on the left side, I get a 7. On the right side, 16x minus 15x is just 1x, or we just write that as x. Okay, so now let's do these next two. And maybe I'll leave these solutions on the screen. Put these next two on the screen that we'll be working on now. And then if you want to work ahead, we'll take maybe about 6 minutes to go through these next two. because they have some several distributive properties and things. And then if you're, done before the 6 minutes is up, you can start in the next one or two. Okay, so that 6 minutes is about up. So let's take a look at these two problems. So again, there were, quite a few steps in each of these problems. So if you didn't get through them all in 6 minutes, if you got, pretty close, you're, pretty close to the pace. And as you get more comfortable with this, things speed up a little bit. And if you got through both of them in 6 minutes, you're, well on pace. So good job. And as always, if you get through a problem and you feel like you have a little bit of margin, if you get through, say, these problems in 4 minutes, if you went, faster than the typical, use that time wisely. Don't, finish the problems and then just, play on your phone or something for the other 2 minutes. Go back and check your solution, right? Take your solution, plug it back in, and double check that the solution you got is the correct solution. So train yourself now to use those good test taking strategies. And, that can be the difference in a letter grade. If you catch two or three errors and problems that you might not have otherwise caught, that could boost your grade on an exam from a B to an A, from a C to a B. So just doing that extra couple of steps, that extra, little bit of extra diligence, can be really helpful in the practical side of things too. But let's go through these problems. So we have 5x plus 27 plus 9x plus 14x minus 22. We have 14x plus 27 equals 14x minus 22. And now I see something interesting happens. If I try to isolate my variable term, and I maybe not write the plus, it's not terrible to write a plus sign in front of a positive, but I end up getting a quote solution in some sense. Or in other words, I end up getting an equivalent equation to the initial equation that is 27 equals negative 22. So I have some equations, like say this one up here, where I say this initial equation has a certain value or possibly values of x that I can substitute in that yield a true statement, where the left side and the right side end up being the same number. The point of these equation solving steps is to get to a simpler looking equation like x equals 7. And I can very clearly see, I can trivially see now that plugging in 7 for x is going to be the only solution to this. If I try to plug in 8 for x, I get 8 equals 7. Clearly, that's not a true statement. So the set of solutions to my initial equation are the same as the set of solutions to my simpler equation. Now let's take that thought and apply it here. The set of solutions to my initial equation are the same as the set of solutions to my simpler equation. Is there any x that I can plug in this simpler equation, in this one at the bottom, to yield a true statement? Is there any value of x I can choose to make 27 and negative 22 the same number? Well, of course not. I don't even see any x's in here. Changing what I choose for x doesn't change this statement at all. 27 is never equal to negative 22. This is always a false statement. It's always a contradiction, but it has the same truth value as my initial equation. This is always a contradiction. It can never be true for any x. So this has no solution. There is no value of x that I could plug into 27 equals negative 22 to yield a correct equation, to yield a true statement. Therefore, there's also no x that I could plug into this initial equation to yield a true statement, where the left and the right side would represent the same number. So the answer here is no solution. How would I check my work on a no solution kind of problem? I kind of just have to go back through and just double check all my steps and make sure that I didn't make a mistake. Right? I don't have something tangible like x equals 7 to plug back in and get 5 equals 5 or something like that to verify. So on a problem like this, the way that I would check is I would just go back through carefully and check each of my steps. Okay, so let's go down to the next one. We'll start on the left side, and we'll start in the innermost parentheses. So I have 5 times 2 plus 12 plus 8t. And then the right side I can simplify a little bit as well. 5 times 8 is 40. T minus 50. Let me take one more step and simplify this left side. So 12 plus 2 is 14. I'll distribute. 5 times 14, I can use that same kind of thing. I can think of 5 times 14 as 5 times 10 plus 4. Or in other words, it's going to be 50 plus 20 is 70. 5 times 8 is 40. And again, if I subtract 40, t from both sides, I get 70 equals negative 50. Again, for the same reason, I get no solution. This is one thing to think about as a test-taking strategy as well. A lot of times we have a preconceived idea of what we think the answers should be on a test. A lot of times, maybe we're locked into, all right, I need to get x equals some number. Or maybe we just reviewed the section for these contradictions and identities, these no solutions or all solutions. Where did the 50 come from? From the 5 times 10. So when I distributed the 5 across to this 10. Yeah, so a lot of times, if we just reviewed this section, we might think, okay, there's got to be like one contradiction and one identity, or there's got to be one no solution and one all solutions. That's not always the case, right? In this case, we had 2 no solutions and no instances of all real numbers or all solutions. Now, if instead we had a situation where we ended up with plus 70 here, if this had been instead of, say, a minus 10, if it had been a plus 14, then I got a plus 70, a plus 70. So in this situation, if I had a plus 14 up here instead of this minus 10, I would have gotten to the end. And I would have ended up with a statement, a claim, an equation, 70 equals 70. And then I can say that the value of t that I can choose to make this a true equation in red down here is the same value of t that I can choose to make this initial equation true. Well, but 70 equals 70 is always true. I could pick t equals 1 or t equals 100 or t equals negative 1,000. 70 equals 70 is always a true statement. So this bottom statement will be true for any t. Therefore, the initial equation would be true for any t in this revised example. So in this case, I would say something like all real numbers would be solutions. I can choose t to be any number because 70 equals 70 is always true, regardless of how I choose t. Then regardless of how I choose t, this first equation will always be true. So I just wanted to go through that alternative example just so that we have an example of an identity of a statement that is always true, just so that we see another one in the review. But again, sometimes test taking strategies are something that are maybe focused on a little bit less, but we want to keep these test taking strategies in mind. We don't want to have preconceived notions about, should I always get a nice number for my answer? If I got x equals 17 thirds or something, like that's not such a nice number, but I don't expect to always get nice numbers for my answers. Should I always expect, exactly one of each kind of problem on an exam? Maybe not, right? So I don't want to go into an exam with these preconceived notions and then get flustered if I get, say, 2 no solution problems in a row. That doesn't mean necessarily you did anything wrong, especially if you're checking your work and you checked your work and your work looks good for both of them, then go with it. Okay, so I guess I don't need to move those too far down just yet. So these next 2 problems, fractions and decimals, everybody's favorite. But if we remember how to approach these, I think we remember that they're not that terrible. So let's take 5 minutes to go through these 2, and then we'll come back and we'll discuss them. So 5 minutes for these next 2. And as always, if you finish early, you check your work. If you finish checking your work and you're still early, you can start in the next couple. And if you don't get through all of them in 5 minutes, that's okay. There's still plenty of time to, work up to speed and get used to the material. Okay, let's work through these two. So in the first problem, we see we have fractions as coefficients and as constant terms. So the first step that we want to do is to clear the fractions. Even if you're good at working with fractions, it usually is still a good first step to clear the fractions because that just makes all of the intermediate steps easier and more streamlined. Um, so even for somebody who's comfortable with working with fractions on each step, it's usually just less of a hassle to clear the fractions first. So we look at our denominators. We see a 7, a 4, and a 14. So we come over here, we need to first find the LCD, the lowest common denominator. We start by writing each of our denominators. And then we get a prime factorization. So 14 is 2 times 7. 2 and 7 are prime numbers, so 2 times 7. And remember, I think now that I have like a first twos column, I have a first sevens column. So what is 4? 4 is 2 times 2. It has a first 2. It doesn't have any sevens, but it has a second 2. So I now have a second twos column that was contributed from the 4. And then 7, well, 7 is already a prime number, so its prime factorization is just itself, 7. And that goes in the first sevens column. And then my LCD, I have a first twos column, so I write a 2. I have a first sevens column, I write a 7. I have a second twos column, so I write a 2. Or this is 4 times 7 is 28. So my very first step, I multiply by 28 on both sides. As an aside, when you get more used to finding these LCDs for a problem like this, you might be able to do it in your head. One quick way of doing it is to take kind of your biggest denominator, 14 here. I know my lowest common denominator has to be a multiple of 14. So it has to be 14, 28, 42, something like that. And then I just ask myself, do both 4 and 7 divide evenly into 14? Well, 7 does. 7 is 14 times 2, or 7 times 2 is 14. But 4 does not. Okay, what's my next multiple of 14? 28. 7 goes into 28, of course, because it goes into 14. Does 4 go into 28? Yeah, 4 times 7 is 28. So there we go. Right. So you can find these LCDs more efficiently when you get more used to finding them. And that's, one quick way to do it. Take your biggest denominator, check its multiples, and just see as you're going up, what's the smallest multiple of the biggest denominator for which each of the other denominators divides into it. If you're not used to finding these, that's a little bit of a jump in difficulty. So you just use this pattern that we have over to the right here. But when you get used to it, you can take some shortcuts. But again, we multiply by 28. (28) times 5/14. Maybe I'll do one more step here. (28) times negative x is negative 28x. And here, 28 times 5/14. Remember, this 28 is like 28 over 1. And think of it that way. And I see that I have a factor of 14 in both the 14 and the 28. So this ends up being a 10x. This factor of 4 divides with the factor of 4 and the 28, leaving me with 7. negative 28x does not need any simplification. And this 7 divides with the 7 and the 28, leaving a 4. I'll add 28x to both sides. This will get my variable terms on the left side with my largest coefficient so that I have a positive coefficient. And then I'll isolate my variable term by subtracting 21 from both sides so that these go away. I get 38x equals negative 21 plus 4 is negative 17. Or x equals negative 17 over 38. That is my final answer. And we have a similar process down here. We have decimals, which are kind of like fractions, right? These are like fractions where we have integer divided by 10 or divided by 100, something like that. So how many decimal places do I have in each of these? I have 1, 2, 0, and 2. So max decimal places that I see is 2. I need to move the decimal point 2 places to the right everywhere in order to get rid of all of my decimals. To move my decimal point 2 places to the right, I multiply by 10 squared, aka 100. Now, if I distribute 100 times 1.5, and just a reminder, 100 times 1.5, well, 1.5, I want to move this decimal point 2 places to the right, but I only have one visible place right now. But 1.5 is the same as 1.50, just giving me another place to envision moving that decimal point one more to the right. So this is going to be 150x minus 275 equals 100x minus 325. Kind of big numbers, but it's not too bad. We subtract 100x from both sides. Same process as before. The numbers are a little bigger, but the process doesn't change. I add 275 to both sides. 150x minus 100x give me 50x, and these go away, equals 100x minus 100x goes away. So 275 minus 325, I can think of that as a negative of the answer, and then switch the order. And by switching the order, putting the bigger one first and the smaller one second, sometimes that just makes it a little easier to see what the subtraction is going to result in. And I see this as 50. So 50x equals negative 50. We now isolate the variable. And I get that x equals negative 1. I could go ahead and plug that back in and check, do a little bit of decimal arithmetic, and check that the left and right sides are equal, and they should be. Okay, so for the last little bit of class, let's take a look at these last two problems. We have a problem on solving an equation that has more than one variable in it for a specified variable. So solve this equation, 3x plus 4y equals 12, solve it for y. In other words, I want to get y equals a bunch of stuff. I want to get the y by itself. And then solve this inequality and write your answer in all three of the notations: algebraic notation, interval, and graphical notation. So we'll take about 5 minutes for these problems, come back and work through them, and that will wrap up class today. So for these last 5 minutes, give it all you got. These are a couple of tough problems, but I think we can work through them. Okay, it's about 5 minutes, so let's work through these last two problems. So I gave a little hint up here that since we're solving for y, we're kind of thinking of y as the variable and kind of thinking, at least for right now, of everything else as constants. So this 3x term, we're really kind of thinking of it more like a constant term. The 12 we're thinking of as a constant term, and the 4y we're thinking of as the variable term, with y being the variable. So what is our first step? We want to isolate the variable term. We only see the variable in one place, so the variable term, we don't need to move any variable terms, but we can move this so-called constant term to the other side to get 4y equals negative 3x plus 12. So this isolates the variable term 4y. And now we want to isolate the variable. We want to get the y by itself. We do that by dividing by 4 on both sides. We have to be careful on the right side. We have to divide the entire right side by 4. So on the left side, we just get y. And on the right side, we get 1/4 times negative 3x plus 12. And I'll distribute this just to make it look a little nicer. One-fourth of 12 is 3. So this will be kind of an important idea later on, being able to manipulate these, in this case, linear equations in two variables, being able to solve for one or the other variable as we need to. So this is an important thing to be able to do later on in the course. And then lastly, we have an inequality here. 4 minus 5x is greater than 3x plus 1. And let's work first towards getting an algebraic solution, and then we can interpret that graphically and as an interval. So we need to get our variable terms together. We need to isolate the variable term. And again, I look at my variable terms. One has a coefficient of 3. The other has a coefficient of -5. I'll move the one with the smaller coefficient. And negative numbers are always smaller than positive numbers, so I'll move the negative 5x to the right side by adding 5x to both sides. I'm going to put my variable terms on the right side. So I want to get my constant terms onto the left side. I do that by subtracting 1 from both sides. My inequality has not changed direction. Plus 1 minus 1 goes away, and I have 8x on the right side. 5x minus 5x goes away. 4 minus 1 is 3. So I have 8x is less than 3. Now I isolate the variable by dividing through by the coefficient of the variable. These go away. And I get x less than 3/8. Note that I did not need to change the sign here because I divided through by a positive number, a positive coefficient. And I got a positive coefficient because I actively chose to put my variable terms on the side that would give me the positive coefficient. That's why I moved the smaller coefficient to the larger, because that way I always end up with a positive coefficient. And again, could you do it the other way? Sure. But then there's just one more little chance for an error. There's one more thing that you need to remember, one more chance for a mistake. And if we can avoid complexity, if we can avoid additional chances for mistakes, that's usually a good thing. So here we have x less than 3/8. We could also write it this way. So I have 3/8. I have an open bracket and open parentheses because I do not want to include 3/8. If I did want to include 3/8, I would use a closed bracket, a square bracket like this. And then since x less than 3/8, my arrow points to the left. And remember, I always think of minus infinity being kind of all the way to the left and plus infinity being all the way to the right. So this interval is minus infinity. Minus infinity always gets an open bracket, a parentheses, because we can't actually include minus infinity, up to 3/8. And I do not want to include 3/8 because, again, this is a strict inequality. So that's my interval notation. Are there any questions on anything from the review? Anything from section 2.7 inequalities that we talked about, or really anything from chapter 2 at all? Okay, well, I'll be in office hours. We'll end class just a couple minutes early today. I'll pop into office hours a couple minutes early, so give me 5 or so minutes to get things kind of switched over. And then I'll be in office hours. If anybody has any questions, if you want to pop in there, give me 5 minutes or so just to switch things over, and then you can pop in. Otherwise, I will see you all on Thursday, where we'll start chapter 3. So again, good idea to just kind of pre-read the next couple of sections, have an idea what we'll be covering Thursday, and then we'll come back on Thursday starting that new chapter. So I will see you all on Thursday.
Thank you. Have a good day.